Hello and welcome. I am Sanjeev Sharma and I represent Melior Structure Solutions. We are specialized in precast structural design of buildings. Today I'm going to cover structural design of precast high-rise commercial building as a case study. The project is a commercial building with 4 basements, ground plus 24 stories above ground. As you can see in the plan, it is approximately 200 meters long, 34 meters wide, and 110 meters tall above ground. It is designed as full precast building above foundation, though later suited to be constructed with cast in situ columns and walls above 6th floor due to construction constraints. The screen shows the list of the design codes that has been followed. It covers the Indian codes for the loading, for the concrete design, for the seismic loading, the code for the tall building, and where information in Indian codes is insufficient or unavailable, following international codes are referred: ACA 318, which is for the concrete structure, and PCI design handbook. So the concrete strengths for the structural elements is listed here. Typically columns have higher strengths at the lower levels and it's reduced at the upper levels. Beams which are pre-stressed has 50 MPa, non-pre-stressed has 40 MPa. Walls also, like columns, varies in strength from 40 to 70 MPa. All pre-stressed elements are minimum 50 MPa. Reinforcement FY 500 MPa is a grade that has been used. So here's a list of the live loads that are considered for the design, and these are as per IS 875 and also as per the utility of the area. So the earthquake load is applied as per Indian Code IS 1893, seismic zone 2. These are the factors that has been listed. Wind loads were applied as per the wind tunnel test outputs that were carried out by a specialized agency specific to the structure, this structure. So this slide shows the typical layout. As you can see, the upper plan shows a typical floor plan, and being fairly long, 200 meters, it has been divided into 2 towers separated by an expansion joint. So for the analysis purpose, 2 separate analyses were done for each of the tower. We can see on the lower half the left part of the building, and the arrangement is typically a hollow core slab as a floor system, beams and in the perimeter and in one direction in the middle supporting these hollow core slabs, columns supporting the beams, walls, and the central area with which is basically the core slab, the central core and lobby, lift lobby, staircases, etc. The structural system for the gravity loads consists of hollow core slabs and cast in situ structural topping. The hollow core slabs are pre-tension slabs, so they can go long spans with lesser thickness. The precast beams and walls that support the floor slabs are provided. We're going to explain them in more detail in the coming slides. The precast concrete columns, they support the beams, and columns and walls together, they transfer the gravity loads to the foundation. So together these 4 elements constitute the gravity load resistance. The lateral loads are mainly resisted by the walls and to some extent by the moment resisting frames. The structural concrete topping is provided to act as diaphragm in order to transfer the lateral loads within the horizontal plane to the shear walls and moment resisting frames. The design methodology, if we start with the floors, as we can see here, the precast hollow core slabs spanning one way are supported on the partially precast pre-tension beams forming the floor system. The hollow core slabs are voided slabs and are typically 1.2 meter wide. They have a shear key profile at the edges, and they are laid next to each other as a one-way spanning planks, and there is a reinforced cast in situ structural topping over the hollow core slabs that act as composite with the hollow core slab in resisting the gravity loads, and that topping also acts as diaphragm connecting the shear walls, thus enabling resistance against lateral forces from wind and earthquake. Coming to the beams, they are partially precast with top 150 mm left without casting but with projecting stirrups. Now, after erection of hollow core slabs on these beams, the top reinforcement is placed at site in the top part. Reinforcement is continuous over support and gets integrated with the projecting column reinforcement, thus forming the moment resisting frame. So these frames are in one direction, as you can see in the image. So the connection is stitched at site, cast in situ, but once the connection is done and the top part of the beam is cast, then the full depth of the beam is activated and they act as a one-way moment frames. So next coming to the vertical elements, the columns and shear walls are collecting the vertical loads from the beams at each floor and transfer them to the foundation. The columns, mainly they collect the gravity load, and the shear walls also provide lateral stability against wind and seismic forces. The connection details on the right are blown up and for clarity, and the arrows show where this detail is applicable to the structure at site. Similarly, the wall slab connection is blown up to show how the wall-to-wall connection is made and where it is applicable at the site. As far as the foundation and retaining walls are concerned, they are cast in situ. The foundation system is isolated foundations under the columns and mat foundations under the shear wall and stair walls, lift core walls. The retaining wall has a strip foundation below it. All the foundations are connected with a stitch slab at their top, forming a watertight base. This stitch slab is important because it's a basement structure and there is chances of water seepage happening due to floods, due to rainwater seepage, and to avoid that penetrating into the basement, another stitch slab at the top is provided with waterproofing. So we discussed the gravity loading, we discussed the lateral loading, and this is a summary of it, basically, that the sizes that we typically arrived for this building. So since the hollow core slabs are spanning around 10 meters, and for the live loading of 5 kilonewton and 10 kilonewton in some areas due to server, 250 hollow core is provided for the car park and office areas, and 300 hollow core thickness for the machine room areas is provided. The structural topping is mostly 85 mm in all the areas, because for longer spans there is a camber also in the slabs, and to cover that and to embed the services, MEP services, 85 mm of the thickness is recommended. In some areas where heavy loading is there, we have increased the topping and provided up to 185 mm. Precast beams are typically 1400 wide, including the nib or the ledge for supporting the hollow core slabs, and they are 600 deep in total. So the precast part is 450 mm and 150 mm part is done at site with cast in situ concrete after placing the top reinforcement. The columns are typically 1.4 meter by 1.4 meter up to podium level, which is ground floor. Then from ground above up to 15th floor, they're reduced in size from 1.2 to 1.2 meter, and above 15th floor, they are 1 meter by 1 meter. And also the grade of the columns are reduced as we go up in this level. The lateral loads from wind and earthquake are resisted primarily by shear walls in both directions and nominally by moment resisting frames. Structural concrete topping is provided over precast floor slabs to act as diaphragm in order to transfer the lateral loads within the horizontal plane to the shear wall. The RCC walls are 250 thick and 200 thick up to level 3, and 200 thick from level 3 onwards. There are some outriggers provided on the perimeter for stability. There are 350 thick. The very important part of precast design and construction is connections, because each element is produced individually in the plant, is shipped to site, and at the final location they are assembled to give a monolithic equivalent effect. So precast hollow core slabs at the edges have shear keys that distribute the local loads over a larger area, similar to monolithic construction. The reinforced structural topping over the slabs further assists in the same. The U-bars connecting the topping and shear key assist in composite action and avoid diaphragm buckling. So it's important to have a shear key, and the hollow core shape comes along with it. And if you have a U-bar within the shear key with the topping, so that bonds the topping and increases the bonding between the topping and the hollow core, that assists in composite action as well as the next connection is hollow core slab to beam connection. This is a very simple connection. The hollow core simply sits on the beam ledge, on a leveled ledge, and the cast in situ topping is done over it after putting some reinforcement in it. The reinforcement of the topping penetrates into the beam, and sometimes we also place one rebar every joint of the hollow core slab, which comes at 1.2 meter, to avoid progressive collapse of the hollow core slab in case there is a loss of support. So two types of beams are shown there. One which is perpendicular to the hollow core span carrying the hollow core, and the other is parallel to the hollow core and therefore doesn't require a ledge to support the hollow core. Next connection is a beam to column connection, also a very important connection, and this connection is like designed as a moment resistant connection. So the load bearing beams are partially precast and they rest over the column corbels at ends. The top reinforcement of the beam is continuous over the column and thus resisting negative moment formed at the junction. You can note that the beam bottom reinforcement also is connected into the column, forming a unidirectional moment resisting frame. In each direction. So we also have a frame in the other direction, which we saw in the previous slide, and that is basically not carrying the hollow core load, but is participating in stability to some extent. The other connection is a hollow core slab to wall connection. The hollow core slabs rest on the walls with minimum bearing as per code, which is typically 75 mm. In special cases, it can be reduced though. The rebar projecting from the wall is bent into the cast in situ topping over the column to column connection is proposed using reinforcement and proprietary slide sleeve connectors, such as from Dextra for this specific project. The high strength non-shrink grout is filled in the gap that ranges from 20 to 25 mm. The connection is capable of compression, tension, and bending moment. Actually, this connection is equivalent to type 2 coupler. This is a very well recognized connection. Now we come to wall connections. So the wall-to-wall has vertical joint and a horizontal joint. The vertical joint wall-to-wall connection is proposed using proprietary wire loops, as you can see in the image, 3D image shown on the right bottom side. So these walls, they are very easy to make these connections in these walls The wire loops are flexible, they are like strands, so they pop out during erection